Bye.
Well, and ladies and gentlemen, we continue here after the European perspective with our introductory speeches from the next perspective, and that's the industry. Before we do so, I do want to draw your attention again to the chat button that we have in every session, and you might want to just start asking questions. We have more time from now on for discussion, so that's going to be more vivid than when we do so. What are we talking about when we talk about quantum technologies? That's a very difficult but simple question that now will be answered by Mark Mattingley-Scott, who's quantum ambassador, leader EMEA and Asia Pacific at IBM, and deputy chairman of Bitkom High Performance Computing and Quantum Computing Board. Emerging and disrupting technologies seem to be among his true passions when I look at his biography. He supports actively as university teacher as well as on international institutional level. He's even a member of NATO Advisory Committee on Emerging and Disruptive Technologies. Very interesting. And another non-professional passion that he has, I saw, is he's an active musician and a radio amateur. Mark, well, we are on video today, but I'm sure we will hear you at some point also. Maybe you have a podcast or something as well. The floor is yours for now. Great to have you here.
Thank you very much for the introduction. When I say I'm a musician, I'm an amateur musician, and I will spare you all the torture of the music I play. Thank you for the introduction, and I'm sure you're all have your various personal experiences and personal relationship to quantum computing, or perhaps you're completely new to it. So the question about what do we mean when we talk about quantum technologies, what makes them so different, what makes them so special is probably very relevant and certainly deserves some attention at the start of this conference. When I was elected to the board of the Bitkom working group on high performance computing and quantum computing back in 2020, I promised to push for two things. The first was to establish a yearly quantum summit, akin to the Big Data Summit, which we instigated in the Big Data and Advanced Analytics Working Group in Bitkom in 2013, and to motivate the members of the working group to write the definitive book on quantum computing in Germany. Providing the impetus for something and actually doing it, as we all know, two different things. And thanks to the tireless work of the Bitkom staff and subsidiaries, and above all, the active members of the working group and my fellow board members, we were able to turn what was an idea into the event we are kicking off today. And I hope it will become a milestone quantum platform, which is blocked in everyone's calendars in the years to come. I want to express a personal thank you to everyone who made this event possible. The working group consists of interested individuals from Bitkom member companies who are prepared to devote their free time to drive digital technologies in Germany. In the case of quantum technologies, something which is going to be key for our economic future. The Quantum Summit's goal is to examine the entire range of quantum technologies, from quantum metrology and quantum communication to quantum computing. We would like you, at the end of the day, tomorrow, to go away with an understanding of what these can be used for, to understand their potential for industrial exploitation, and to understand how we might use them in a beneficial way. One of the key questions is, why is quantum special and different and new? When we talk about quantum technologies, what do we mean? What specific technologies are we going to be discussing? And perhaps most importantly, the question of what role might Germany play in the development and industrialization of the various types of quantum technologies. To begin to understand quantum technologies in the wider sense, we need to have a reference point. And in our case, this will be how quantum differs from classical, and more precisely, how quantum mechanics differs from classical mechanics. Classical mechanics tells us how an internal combustion engine works, how my laptop works, how the weather works. Add in a touch of general relativity, and it tells us how the planets and the stars and galaxies move. But if we add a tiny little bit of special relativity, we start to see the hints of a problem. Quantum mechanics is fundamentally different, really deeply, inherently, and counterintuitively different. The great physicists of the late 19th and early 20th centuries discovered that at very, very small scales, and I have to apologize in advance to all the combustion engineers, chemists, electrical engineers, biologists, climate scientists, and astrophysicists for using the word clean here. The clean world of classical mechanics no longer behaves itself. At very small physical scales, there is no certainty, only probability. There is no such thing as an observer and observed. There is no objective reality. Everything is undetermined, a chimera, until we actually look, and only then do things become definite, fixed in some way. The evidence for this mounted in the late 1800s and inevitably led to the acceptance of three core principles. Firstly, the properties of things are quantized. There can only be certain discrete amounts of things. Secondly, particles can be waves. And finally, waves can be particles, and their equivalence depends on how they're being measured. In other words, how we choose to interact with them. Over half a century after Einstein's paper on the photoelectric effect launched the quantum revolution, the first tentative steps were made in its exploitation in computing and in metrology, the science of measurement, with the invention of the laser and the proof that non-reversible computation increases the entropy of the universe. The laser ushered in the age of coherent photons, and with it the ability to precisely measure and define the world, and to communicate with a precision and accuracy that was unimaginable up to then. Since those first tentative steps, we now have the means to harness the quantum nature of light, and how to harness the quantum nature of electrons and atoms. Germany leads the world in pushing the boundaries of what can be achieved in both quantum communication and quantum metrology. The ability to use entangled quantum photons to communicate and to interact with our world and tell us about its properties. We can be proud of this and of the boldness of the people and organizations who thrive in this area. Our understanding, pioneered by Alan Turing in 1936, of what a computational machine could do, what kind of problems it could solve efficiently, what kind of problems it could not solve, assuming different variants of Alan Turing's simple machine, parallel Turing machines, probabilistic Turing machines, and other variants. It became clear also in the early 1960s, when Hartmanis and Stearns brought the idea of computational complexity classes to the world, that there was a whole different universe of computation out there. The stage was set back then, as it were, for quantum computing to be born. Through a key insight in 1974, that every computer program can be rewritten so that it is reversible and thus potentially not violate the observability constraint of quantum mechanics. We saw in 1981 a physicist, Richard Feynman, and others, who showed us that there are problems in quantum mechanics which, despite being horribly inefficient to solve using classical computers, would be highly efficient if solvable on a computer based on those same quantum mechanical principles. 13 years later, an MIT researcher named Peter Shor wrote an algorithm which showed a way to not just simulate quantum mechanical systems, the basis of physics, chemistry, biology, in fact, all material things, but also to solve a difficult classical algebra problem in an exponentially faster way than a classical computer. Exponentially faster means, for example, that if the time to calculate a solution on a classical computer increases with the power of the size of the problem, a quantum algorithm where the time to calculate a solution increases to some fixed power of the size of the problem will be exponentially faster. This is a key metric, and you will see mention of this everywhere in quantum computing. Although factoring, for example, a 2000-bit number would take billions of CPU years on our fastest supercomputers, with a few thousand error-corrected qubits and Peter Shor's algorithm, this might one day only take a few weeks. In all discussions of quantum computing, you will hear this speed-up discussion. Is it exponential, quadratic, or approximate? Take this away, this is a key metric in quantum computing. And it is a subject of a great deal of the ongoing research work in quantum algorithm design. Later in the same decade, the first qubits, the simplest measurable and manipulatable quantum mechanical systems, were ushered into the world. The race to develop a viable qubit was on, and at the end of the 1980s, a way was found to use quantum tunneling to solve a particular type of optimization problem in quantum annealers. And in the 2000s and finally the 2010s, we have seen the availability of the first universal quantum computers, which implement qubits and quantum gates, and which can be used to test our ideas and develop more powerful algorithms. We now know that there are problems which will always be more efficient on a classical computer. We also know that there are problems which will be more efficient on a quantum computer. And there is a question mark about some problems which may fall into one or the other side. For those problems where we know that quantum computers are more efficient, we are still not at the point where the number and quality of the qubits is sufficient to actually beat classical computers. But that point is approaching fast. And from my own personal point of view, it appears to be accelerating towards us. Looking to the future, we can see the potential of these technologies slowly becoming more clearly defined through the barriers we've already broken through and those we have yet to overcome. We know that quantum metrology will revolutionize non-invasive medical diagnosis. It will revolutionize the measurement of the world in all its facets. We know that quantum communication will redefine what it means to communicate, especially what it means to communicate securely. And we know that quantum computing has the potential to revolutionize computing and allow us to solve whole classes of problems significantly faster than is possible today. What role does Germany have to play in all this is a question you are all hopefully asking yourselves, particularly as it is the core objective of this conference. If you look at the history of quantum mechanics, then it is dotted with German, Austrian, and Swiss names. Perhaps the greatest among them being Max Born, although his story also directly relates to the darkest part of Germany's history, reminding us that no technology can be held back, and the only way to ensure benevolent use is to ensure transparency, be ever vigilant, and mandate consensus. And I think Germany can take on this task. Today, if you try to enumerate all the university research groups in Germany who are working on some aspect of quantum technologies or their use, you will have a difficult job. It is obviously a countable number, but it is probably around 4 digits. That's right, we're 1,000 in one country. No other country on earth has that density of academic commitment to this technology. If we look to the commercial exploitation of quantum, however, there is a more differentiated picture. In the world of optics, in which Germany has a long tradition of being the best in the world, and which leads naturally to the question of industrialization of quantum metrology and quantum communications, we are the leaders. There are small niches where this might not be the case, but finding a systemic, viable, competitive region is not possible. Not in Japan, China, Korea, Taiwan, USA, nowhere. Germany leads. In the case of quantum computing, the German government has allocated over 2 billion euros to, among other things, the development of 2 viable quantum computing technologies within the next few years. Notwithstanding collaborations with multinational, European, and regional ecosystems, and initiatives to piggyback on efforts from other countries to bootstrap this process, it is a tall order. I sincerely hope it is not too late, because it is quite clear to me that the long-term impact of quantum technologies will match or even exceed those of the mobility revolution started here in Germany over a century ago. We are not talking about the next, we are talking about the next true industrial revolution. We are not talking about better, faster, smaller, networked, although these alone have fundamentally changed the global economy over the last few decades. We are talking about something which has never ever been before, something which we cannot even directly perceive. A shadow play where we can see the action but not the actors. Germany needs to leave. It is imperative. One encouraging point is very clear to me, though. Every quantum technology, whether communications, photonic metrology, or one of the many ways of constructing qubits, all of them require either the highest level of skill in developing electronics, and even IBM develops their control electronics here in Böblingen, or in developing mechanical and optical systems. And on this point, Germany leads the world by miles. There is literally no other place on Earth where there are so many first-class engineers. If you go into the deepest, remotest hillside village in the Swabian Badlands, where I am today, poke a stick at someone in the local Besenwirtschaft, and you will hear, "Hey, that hurt, I'm an engineer." This doesn't occur anywhere else on Earth. All this may sound a little bit strange coming from the mouth of a Brite, but one day, after the collective decision by the United Kingdom to abandon any vestiges of sanity and leave the European Union, I applied to become a German citizen, an economic migrant when you get down to it. I consider myself extraordinarily privileged to be able to say I am German. So I have a considerable vested interest in quantum becoming an even bigger German success story than the automobile. Please join me today and tomorrow in helping to make this happen by learning, listening, asking questions, and finding new friends and collaborators, and discovering what role you have to play in the coming revolution. Thank you.
Well, thank you very much, Mark, and well, happy to hear your favor of Germany so much. We do have a first question from our audience, actually, and well, someone wants to know what is an example of a problem where a classical computer is superior. Could you answer that, please?
Yes. So multiplying two numbers together, for example. If you try to multiply 3 times 5 to get 15, classical computer is very, very efficient at doing that. If you try to reverse it, and you're given 15 and you're trying to determine what the factors of 15 are, a classical computer is appallingly bad at it. And Shor's algorithm is very efficient. There are a number of cases of where you have similar differences.
Well, thank you for that. When you've talked a lot about the academic expertise that we have in Germany and the engineers and well, all our great potentials, but well, what we always lack a little bit here is that maybe that spirit to bring things into application. How would you would you have an idea of how to change that spirit around a little bit?
Actually, you don't lack the spirit. A lot of the true innovations that have happened to humankind, Germany has played a significant or leading role. I think it's necessary to acknowledge and to speak openly about Germany's strengths. There is a tendency perhaps not to do this, to be a little bit ashamed for historical reasons. Speaking as a British person, I can perhaps say that. I think if you look at industries like quantum optics or optics in general, this is a real example of Germany leading through innovation over decades, centuries. I think that spirit of we can do this, we can lead, that's something that is there. The potential is there, and of course, what needs to happen is that the Swabian village in the Badlands, the company there working on electronics, working on technologies which will become key, need to pick up the baton and take the lead. It's very easy.
Oh, very, very good to hear that. Actually, if we did a commercial on Germany, I would, I would suggest you would take a role in that. Well, anyhow, when you describe Germany's areas of, let's put it, exploitation, or Germany's areas of expertise, what should be areas of expertise for the EU to, conquer or to work on, in your opinion, and what are parts that we better leave to the world?
I think there is absolutely nothing we had better leave to the world. There is zero, and my IBM colleagues are probably going to lynch me for this. I think in Europe we have a critical mass, both in the ability to develop, implement, engineer quantum technologies, but we also have a significant critical mass in applications. And by applications, I'm not talking about Peter Shor's algorithm, I'm talking about industries. We have German, Swedish, Italian, French industry. We have I mean, over half the world's pharmaceutical companies are in Central Europe. In every industry you look at, either in Germany or in Europe, we have a significant market share or are leading those markets. And those are the areas where quantum computing will be applied, will make a huge difference, will change industries, will change the way we solve problems, will completely change business models. It's just all that is necessary is to acknowledge that, to begin to explore quantum computing within ecosystems, with technology providers, determine how to use quantum technologies, not just quantum computing, but quantum technologies in general. And then Europe can lead.
Mm-hmm. And when we look a little bit into the future from now, let's put like maybe 5 years. What would you say would be the top applications or the leading applications?
This is
just your opinion. That's what I.
It's very, very difficult to answer that. I think if here I can speak as an IBMer. If we have publicly stated that we will achieve 1,000+ qubits by 2023. 2023, in case you didn't look, is a year and a half away, or at least it starts in a year and a half. So we've said by some point in 2023 we'll be over 1,000 qubits. That's a very aggressive target, and IBM doesn't make those kind of statements lightly. That we're good, that's a commitment. So from the hardware point of view, that's an interesting number of qubits. What exactly can you do with those qubits? Which problems exactly can you solve? I really can't say, because to answer that question, you need somebody from an industry, somebody with an industry problem, somebody who's looked at that number of qubits and said, okay, now these are the kind of problems I can solve. So, and that's what I meant with the ecosystem discussion, with your question as to what can Europe do. That dialogue is essential. To be able to answer that question, we need that dialogue, and we need that dialogue to be really moving forward.
Mm-hmm. Well, since we have no more audience questions and we have a couple of minutes left, I'd just like to ask you one thing that I mentioned in the beginning. You're being part of the NATO Advisory Committee in emerging and disruptive technologies. Can you tell us a little bit about your work there?
Yes, so I think it was about a year ago, I was invited to join this group of 12 industry and academia experts advising the NATO Deputy Director General on ways to leverage, exploit, and become better at using emerging and disruptive technologies. Military organizations are typically have a very high inertia in adopting new technologies, and often get locked into procurement and innovation dead ends. So NATO said we need to do something about that. They've begun a number of initiatives, including the establishment of this group of experts, of which I am a member. And a couple of months ago, we published our interim report, which is publicly available on the internet, where we recommended a number of specific measures which we thought NATO should take. There was a vote on that in the recent NATO General Council meeting, I think at the beginning of the month. I can't talk about the details yet because I don't think they've been made public, but there is some hope, some potential for innovation within NATO. And I think particularly in the role of NATO as a stabilizing factor in international relations. I think that's very important.
Mm-hmm. Well, thank you very much. A very interesting work that you're doing. Well, on one side on the industry and on the other side on the institutional level. Thank you so much for giving us such a deep insight. I have one last question for you, since our next speech will again be from the institutional, from the political side. We heard the EU, we heard a little bit of the German EU this morning, and now we heard you, or before. What can politics actually do for the industry in that field? If you had like 2 wishes free, what would that be?
Oh, the question has surprised me. Okay.
That was the goal.
Yes. Thank you for that. What can politics do? I think politics can play a key role in the open discussion of the impact of technology. I think politics, the political leadership, aside from questions and issues about their own transparency, which I'm not going to be political, but there's work to be done there, obviously. Leading by example, promoting and pushing a discussion on technology impact, the benefits of technology, also the risks, of course, and how to address that in a consensus way. That's very clearly the job of our political system, our political elite. And then the other thing, of course, is money, always money. How do you do that? What's the best way to do that? What are the most reliable and robust ways to promote technology, new technology? There are best practices we know from our own experiences, but also the experiences of other countries around the world, what works and what doesn't work. And that's a case of just doing what works, which is providing money, but not interfering too much, but also not ignoring things. Kind of a wishy-washy answer, but
well, thank you very much. Not wishy-washy at all, in my opinion. Very open, very clear. Thank you very much. And for all your passion as well for the topic. And we wish you lots of success with all your work further on.